The new High Modulus Masts series will help you step up your game and change the way you ride. I am Mike, brand director at North Foils. Anyone who rides a North Foil has to give this a go. Whether kite foiling, wing foiling, prone foiling, downwinding or pumping, my riding improved so much on my first session. I connected so many more waves than I ever had done before. The ability to carve a turn and hold a rail was amplified. I felt so much more connected to my foil. It was frictionless. I can't personally recommend the HM series enough. Over to Uli to talk more about the design.
Hi, I'm Uli Sommerlatt, North Foil's Product Development Manager. Here to introduce you to our new Sona High Modulus Carbon Mast series. These masts are designed for riders that are looking to get more radical with their maneuvers, make sharper turns and accelerate faster. In our HM range, we have the HM80, the HM85 and the HM105. We also soon will have an HM95. We are using a combination of ultra high modulus fiber and high modulus fiber to achieve our design targets. Ultra thin, ultra stiff. The HM85 has a profile thickness of just 13.5 mm, compared to the CF85 at 16 mm. The HM85 has 67% higher cantilever bending stiffness and 35% higher eccentric bending stiffness and 25% higher torsional stiffness. And this all while having the same weight as the CF85 at 1900 grams. Finding the perfect balance between stiffness and drag is the key ingredient for a high performance mast design. The drag of the mast is influenced by the thickness of the mast, meaning side to side, and the chord length, as well as the profile section that we have chosen for the mast. Different profile sections will result in different drag coefficients. The thicker the profile and the longer the chord length, the stiffer the mast. However, the thicker the profile and the longer chord length also results in increased drag. Therefore, it's important to find the balance between stiffness and drag. This is where high modulus carbon fiber comes into play. It allows us to design a thinner mast section that can withstand the same load as a thicker standard modulus carbon section. Carbon fiber can be broken down into mainly 4 different grades: standard modulus, intermediate modulus, high modulus and ultra high modulus carbon fiber. High modulus and ultra high modulus carbon fiber are created by going through a specialized heat treatment process to remove impurities. In general, the higher the modulus, the stiffer the material. The modulus of elasticity, E, is a measurement of the stiffness of a material and is defined as the ratio of stress to strain when the material is deformed. The higher the modulus, the stiffer the material, or the greater the stress necessary to cause deformation. Improving the performance of the mast comes mainly down to 2 points. That is drag and stiffness. Stiffness we can split up in stiffness and torsion and stiffness and bending. In our mast design process, we define 3 main load cases. The first load case is a bending moment in the mast. The bending moment gets created by a side load pushing at the bottom of the mast, here the geolock area. So a side force coming 90 degrees towards the mast, pushing from the side against the mast and trying to push that mast over. This will create a bending along the mast at the end, trailing edge. With the second load case, we introduce an eccentric bending moment into the mast. We apply a force on the span vise onto the wing pack acting down, like you can see here, such as it would happen when you jump the hydrofoil and land, or when you pump the hydrofoil, you will create an eccentric bending moment to the mast. This means pressure applied to the front wing, here at this location, will result that the midsection of the mast will try to bend in this direction. So if I apply pressure here, you can see that the mast section will try to move out a little bit. In the third load case, we apply a torsional moment to the mast. For this, we apply a force acting on the fuselage, same as load case 1, 90 degrees to the mast, but this time off the center, so at the end of the fuselage, which will create a torsional moment on the mast. This is equivalent to when you engage in any maneuvers on hydrofoil. You will fight the resistance of the water, so the density of the medium, by doing any turns. The ability for your foil to quickly react to that is the stiffness of the torsional flex. Now our existing Sonar CF carbon mast range is one of the strongest and stiffest standard modulus carbon Prepreg masts in the market. However, we saw the potential to further up our game and deliver even higher performance. High modulus carbon fiber is not just a material choice. If you want to design the best performing mast in the market, you have to rethink the design characteristics and break it down what is needed for each discipline. The HM80 favors disciplines without wind power, prone serve, pump and downwind. The shorter chord length over the entire mast length reduces the drag, increases the agility for more glide, more efficiency and quicker turns. The HM80 also enables effortless pumping, be it dock starting or the serve. You will be able to pump for longer and connect more waves due to the reduction in drag. The HM80 has a profile thickness of just 13.5 mm and a chord length of 108 mm. The HM85 covers all disciplines with a focus on wing foiling. Wind power disciplines require edging against the wind to create forward drive. Some of this drive comes from the front wing and some of this drive comes from the mast. To efficiently provide this drive, the chord length in the submerged part of the mast is slightly longer. It increases near the top of the mast to maximize stiffness with no drag penalty, as this part of the mast is clear of the water once up on the foil. A more efficient underwater body shape means less drag and hence higher and easier to reach top end speed. The HM85 has just a thickness of 13.5 mm and a chord length of 115 mm. The HM105 has been optimized for racing. The submerged part of the mast is further 1 mm thinner compared to the HM80 and the HM85, providing reduced drag and maximum top end speed. As a result, this mast is not made for jumping. Like the HM85, the chord length of the submerged part of the mast has been tailored to provide good upwind drive, while the chord length above the waterline increases to provide maximum stiffness. The more efficient shape means faster top end speed and zero ventilation. The minimum thickness of the HM105 is only 12.5 mm, and with that it's one of the thinnest production masts on the market. During the design process, we've paid special attention to the ventilation on the trailing edge and fully eliminated any ventilation on the mast. Ventilation on a hydrofoil mast is when air above the water surface gets sucked down on the trailing edge and causes a vortex that runs down the trailing edge and kills all laminar flow on the hydrofoil. This will result in a massive increase in drag and you will most likely lose control over the foil. You will find all technical specification for each mast size at the bottom of the mast base. In summary, a stiffer mast will provide you with a more direct steering impulse. So when you lean into a turn or give a steering impulse, the mast will have a quicker response. There will be no delay in your steering commands. This allows you to get more radical in your maneuvers, make sharper turns and accelerate faster. The reduced drag will also give you a faster acceleration, greater top end speed and lower bottom end speed. It makes the foil system more efficient, lets you get up on the foil easier and recover faster on touchdowns.